Charlotte Wales 6.3 Numerical Model. Numerical model is a form of quantitative analysis in which we can use to analyse technique and sports performance. Analysing the biomechanics of a technique in this way means that we can advise the athlete to make small changes to their form in order to improve performance and maximise efficiency. Using analytic software allows us to record a technique, and by using a scaling factor, we can obtain information such as distances and angles of the technique. This data can then be used to edit and improve the overall performance. Biomechanics is traditionally divided into the areas of kinematics, which is a branch of mechanics that deals with the geometry of the motion of objects, including displacement, velocity, and acceleration, without taking into account the forces that produce the motion, while kinetics is the study of the relationships between the forces system acting on a body and the changes it produces in body motion. We are looking at the mechanics of movement and force production. The data we have collected is an involved quantitative analysis focusing on distances, angles, and forces. A numerical model is a version that is considered perfect, or the most correct, that you would aim to have all of your athletes performing like. We have previously looked at the perfect shooting technique for basketball. Coaches use a strong performer and compare them to a weaker player and see where the weaker player can improve. A numerical model has to be produced, and this can be done from literature, like coaching manuals, using what they considered the correct way. You can use normative data, which explains things like the average for a specific gender, ability, and age range. It would be unfair to judge the 100-metre sprint time for a group of 15-year-old girls at secondary school against the results of the men's Olympics. There is no logical comparison here, so our models have to be realistic. You can, however, use elite level results, especially for those aspiring to reach this elite level. There are lots of results and data that can be found online, which helps us denote a good model for our athletes to achieve based on elite standards. We used NBA draft data scores. You are also able to use data from a Google blog or a Wikipedia page. However, these resources are much less reliable because anybody is able to write and edit these, therefore they aren't very credible. Overall, the numerical model is looking at the physics of movement and the motion that we can measure and calculate along with the forces. With this understanding, we can look at how we execute skills and how these can be improved. It is quantitative in nature, so it is very objective, where you read a specific number-based measure. We create it by using elite performers, literature, or a combination of both. Forces are a push or a pull that are able to change a state of motion. These are measured in newtons. Forces have 5 different possible effects that can be put onto an object. These 5 elements are rest to motion, change of direction, acceleration, deceleration, and change of shape. By forcefully being moved, an object is taken from rest to motion, meaning it has been moved as the forces around it are no longer equal. If a football is at rest on the ground, its gravitational and reactional forces are equal, and it will not move until kicked by a player. This is in relation to Newton's first law, which I'll expand on the next slide. Forces also have the ability to change the direction an object is moving. For example, in cricket, when a bowler bowls a ball to the batsman, it's travelling straight forward and at speed. However, as soon as the batsman hits the ball with a larger force, the ball is forced to change direction and travel back the way it came and out to the field around. Forces are also able to change the shape of an object, be it pulling a rubber band or kneading dough. If looked at by a detailed camera, when a tennis ball hits a racket or a basketball is bounced off of the floor, it changes the shape of the ball slightly. The force of the ball hitting the hard ground or the racket puts an equal force back onto the ball, meaning that it is forced to bounce back up. This happens because balls are made of an elastic material, which allows them to be squashed or stretched and then return to their original shape. Acceleration and deceleration are opposite to one another. If a force is applied in the direction an object is travelling, then it will cause it to speed up or accelerate. This is shown when you put your foot pressed down on the gas pedal of a car. It is adding a force causing the car to carry on at the same direction, but at a quicker pace. However, deceleration is going to be a force acting in the opposite direction, that is the object moving, forcing it to slow down until it stops. The force isn't great enough to immediately stop the object, but it starts and causes friction. It moves in the opposite direction and slows it down. When the brake pedal is applied in a car, the car is slowly being forced to slow down. There are four types of forces: external, internal, horizontal, and vertical. External forces are forces caused by external agents outside of the system. Internal forces are forces exchanged by the objects within the system. In sports, an internal force is one which is generated within the body, which could be, for example, the leg muscles contracting to move the bones. An external force is one that acts outside of the body, for example, a boxer striking their opponent. Here are some examples of forces acting on a baseball player. Horizontal forces will not affect vertical movement, and the vertical forces will not affect the horizontal movement. The horizontal forces are equal in size and opposite in direction on an object. They are balanced, so the horizontal resultant force is zero. This means that there is no horizontal acceleration, just a horizontal constant speed. If an object is not moving horizontally, then there are no horizontal forces. The vertical forces are equal in size and opposite in direction. They are balanced, so the vertical resultant force is also zero. This means that there is no resultant vertical acceleration. Vertical forces involve jumping and horizontal forces involve running, which is how we assessed it ourselves using a vertical jump and a 20-metre sprint. Small forces are measured with a Newton meter. For measuring large forces like that of a vertical jump, special equipment is required, like a force plate. Sir Isaac Newton wrote 3 laws of motion in 1686. Each of these laws are the basic skills all physicists follow today. The first law is the law of inertia meaning the reluctance to change. The law states that all objects continue in a state of rest or uniform speed in a straight line unless acting upon by a non-zero net force. An object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an outside force. Inertial value is proportional to its mass. For example, the body of a player quickly sprinting down a field will tend to want to retain that motion unless muscular forces can overcome this inertia. Or a skater gliding on ice will continue gliding with the same speed and in the same direction, barring the action of an external force. They will, however, be forced to slow down due to things like friction. Newton's second law is the law of acceleration. The acceleration produced by a net force on an object is directly proportional to the net force, and is inversely proportional to the mass of the object. Acceleration is equal to force divided by mass. For example, when a ball is thrown, kicked, or struck with an implement, it tends to travel in the direction of the line of action of the applied force. Similarly, the greater the amount of force applied, the greater the speed the ball has. If a player improves leg strength through training while maintaining the same body mass, they will have increased their ability to accelerate the body using their legs, resulting in better agility and speed. Newton's third law states that every action has an equal and opposite reaction. Whenever one object exerts a force on a second object, the object exerts an equal and opposite force back on the first. For example, the force created by the legs pushing against the ground results in the ground's reaction force, in which the ground pushes back, and allows the player to move across the court, because the earth is a much bigger force than the player. The player accelerates and moves rapidly, while the earth does not really accelerate or move at all. This action-reaction also occurs at impact with the ball, as the force applied to the ball is matched with the equal and opposite force applied to the racket or the body. Quantities are either measured in scalar or vector values. A scalar value is a quantity that is fully described by a magnitude or a numerical value alone. Vectors are quantities that are fully described by both a magnitude and a direction. An example of a scalar value is a mass, but a vector would be a weight. Distance is a scalar quantity that refers to how much ground an object has covered during its motion. It is not dependent on the location of the object, just its physical distance that is covered. Displacement, however, is a vector quantity that refers to how far out of place an object is. It is the object's overall change in position. Therefore, it measures the shortest distance between 2 points. 400-metre runners that run around a track obviously cover a distance of 400 metres. However, the displacement is zero because they finish in the same place as they started. On the screen, the diagram shows the distance in blue, but the displacement in red, which shows that there is a possible shorter route from A to B. Speed is a scalar quantity. It is the rate at which an object covers a distance. The average speed is the distance covered per time ratio. Speed does not take into account the distance. It is worked out by distance divided by time. On the other hand, velocity is a vector quantity. It is direction aware. The velocity of an object is the rate of change of its position with respect to frame of reference and its function of time. Velocity is equivalent to a specification of an object's speed and displacement of motion. It is calculated by displacement divided by time. Saying an athlete ran at 10 km per hour is a speed, but saying they ran at 10 km per hour westwards is a velocity. Acceleration is the rate of change of a velocity of an object with respect to time. Accelerations are vector quantities in that they have a magnitude and a direction. The orientation of an object's acceleration is given by the orientation of the net force acting on that object. Impulse is the integral of a force over the time interval for which it acts. Since force is a vector quantity, impulse is also a vector quantity. Impulse applied to an object produces an equivalent vector change in its linear momentum, also in the same direction. Momentum is the product of the mass and velocity of an object. It is a vector quantity, possessing a magnitude and a direction. Momentum is mass in motion, and any moving object can have momentum. An object's change in momentum is equal to its impulse. Impulse is the quantity of a force, times the time of the interval. Impulse is not equal to momentum itself, rather it is the increase or decrease of an object's momentum. When measuring a vertical jump, there is an ideal way of doing so, which means that you get a perfect and reliable result. In labs and universities, you can use force plates which are embedded in the ground of the biomechanics lab, and any force that you apply to it, the ground matches, so the plate records this ground reaction force. These force plates take 1,000 measures a second, which leaves you with an incredibly detailed result. Essentially, these work like giant bathroom scales, but from household scales you get around 1 to 2 readings a second. There is an evident comparison here which shows how well these force plates work. If you were to run or walk across these plates, it will record how hard and for how long you have contacted the floor, which is the person's ground reaction force. Newton's equation states that every force has an equal and opposite reaction. So for every force we apply to the ground will apply an identical but opposite force right back on us. When an athlete jumps on a force plate, immediately their force lowers as they bend. The force increases as the athlete breaks near the bottom of the jump and beginning to apply force so that they can change direction and use the ground to propel themselves up. There is no force on the force plate when the athlete is in the air, followed by a big force as they make contact with the plate and a huge braking force. The regular force is then resumed. The force plates give very detailed forces based individually on each athlete's jump. We can measure motion or movement with video cameras. We can see angular motion at a joint using software like Dartfish. These are 2D cameras. There is also the option to use software called Vicom. This is where markers are placed on an athlete's joints so that a computer can generate a 3D version of them. Therefore, the 3D computer image will move exactly as the athlete does, combining all of this info so we can get a lot of biomechanical information. With 2D photos and video collections, the camera must be placed in a very specific position in order to collect the data with a lot of biomechanical information. With 2D photos and videos collection, the camera must be placed in a very specific position in order to collect this necessary information. The setup can take a long time. However, if the time isn't taken, then the data collection will be invalid. The setup of equipment is as important as the experiment itself and often takes longer. Ideal data collection would have the camera at a perpendicular angle, appropriate camera height so that everything was in shot. For example, if a vertical jump was filmed, the height of an athlete's jump would have to be taken into account. This involves setting up the field on view. The spirit levels on the tripod should be taken into account. Also taking into account the distance from the subject. Ideally, a high-quality camera is used with high frames per second capacity to view minute changes. There should also be a fast shutter speed to produce high-clarity images and a lot of light. The fast shutter speed will darken an image, so the more light the better. The shutter speed must also be assessed against this light intensity. If a runner is running from A to B and being timed by a shutter gate, then the camera needs to be set up at the right angle, perpendicular to the direction they're running in. Ideally, there is a 3-4-5 Pythagoras triangle, allowing you to get the optimal position to capture the data. You also need to be able to pan your camera around to follow your athlete if they are running. Perspective error must also be taken into account, so the measurement of angles is accurate.